In the problem SubsetSum, we are given n positive integers w1 to wn, and an integer capital W that is sort of a target value. And the question is whether there's a subset of the input numbers w1 to wn which adds up to exactly capital W. So for example, if we have a set of numbers including the numbers 1, 4, 16, 64, 256, 1040, 1041, 1093, 1284, and 1344, and our target value is 3754, then this is an yes instance of this problem, because we can add up the numbers 1, 16, 64, 256, 1040, 1093, and 1284 to reach the target value 3754 exactly. As always, when our input contains numbers, it is important to note that those numbers have to be encoded in binary. If we would encode them in a less efficient way, we might potentially change the complexity of this problem quite dramatically. So the numbers here are encoded in binary. I claim that 3-satisfiability polynomial time can't be reduces to this SubsetSum problem. So if I get an input for 3-sat, which is just a Boolean formula, I can somehow transform this input into an input for SubsetSum in such a way that the formula is satisfiable if and only if the answer to the transformed instance for SubsetSum is yes. Of course, one problem here is that SubsetSum and 3-satisfiability look like two quite different problems. I mean, SubsetSum is about numbers and subsets of numbers, and 3-satisfiability is about Boolean formulas. So how can we relate these two problems to one another? What you always have to ask yourself in this situation is, what are the crucial properties of the problem that you're reducing from, and how can you sort of simulate those in the problem that you're reducing to? So what are the crucial things for 3-sat? Well, one important aspect for 3-sat are the variables. And this is where the freedom comes in, right? So we can set a variable to true, or we can set a variable to false. And we are somehow asking whether there is a choice we can make here so that the formula is satisfied. For SubsetSum, the decisions we make are also somewhat binary, because we have a set of numbers, and for each of them we have to decide whether to include them in the subset we are constructing or not. So there's also for each number a sort of binary decision here. Once we realize this, the first idea we should have is that we somehow model the variables by numbers, and setting a variable to true should somehow correspond to including that number in our subset. Of course, this is very informal and not at all precise, but we want to start off trying to have some general thoughts about how, in principle, intuitively, a reduction like this could work. In 3-sat, we don't just have the variables, we also have the negation of the variables. And although, in some sense, the negation of a variable is also fixed once we fix the variable, it makes sense here, and actually in many other situations for other reductions as well, to model the negation of a variable explicitly. So we will not just have numbers for a variable, we also have a number for the negation of a variable. So for each variable x and its negation not x, we will introduce a number in our SubsetSum instance. Now, of course, we have to make sure that the solution for the subset sum instance, so the subset we are constructing, would not include both x and not x. That would be nonsensical. So how could we enforce that it's not possible to include both the number corresponding to x and the number corresponding to not x into our subset? The solution is as follows. We construct numbers here for the variables and the negation of the variables. For the variable x, for example, we might take the number 100. And then for the variable not x, we would also take the number 100. And now for our target value, capital W, we would ask that in this first digit position here, the result needs to have a 1. Assume for a moment that we construct our numbers in such a way that if we sum up arbitrary subsets of those numbers, we will never get a carryover. So we can treat each position in the number, each digit, separately. Then, if our target value at a specific position is 1, it means we need to select one number that has a 1 in that position. And only one number, because if we pick 2 of them, we would add them up, and the result would be 2. So if we would pick x and not x, we would get 200, so there would be a 2 in the first position here. So if we want to have any hope of reaching a 1 in the first position, we have to select exactly one of the 2 numbers that belong to x and not x. Either we have to pick x into our subset, or we have to pick not x into the subset. If we pick neither, we will have a 0 where we should have a 1. And if we pick both, we will have a 2 where we should have a 1. In the same way, we do this for all the variables. So we might have some other variable y, and then the negation of that variable, not y. And we do the same thing, just in a different position of the number. So for example, for y, we would take the number 10, and then for not y, we would also take the number 10. And then we have a target value of 1 in the second position here. And the only way to reach that target 1 is to include either y or not y in our subset. Again, if we want to have any hope for our subset to hit the target value exactly, we have to pick one of the 2 numbers that correspond to y and not y. And then maybe we have a third variable, z, and same thing again, just in a different position. So z has a 1 in the third position, and not z has a 1 in the third position as well. And the target there is 1, so we have to include one of those. So this somehow ensures that if we have a solution for the subset sum instance, we can translate this in some way, or interpret it in the 3-set instance as setting variables to true or false, and then also setting the negation of these variables in a consistent manner. The other thing we have in 3-set is clauses. So 3-set, we have a Boolean formula that is composed of clauses, and we want to satisfy all of those clauses at the same time. And each clause is an OR combination of a number of literals. So, for example, the first clause might be not x or y or z, and then the second clause might be x or not y or z, and then the third clause might be not x or not y or not z. So we now need to model these clauses somehow in our subset sum instance as well, and we should make sure that if the numbers we picked in our subset, those belong to some variables, right? That if those satisfy the clauses here, then the subset should sum up to the target value, capital W. But if the subset we selected corresponds to literals that do not satisfy all the clauses, then the target value should not be reached. So how can we encode this into our numbers? We need to further extend the numbers and include additional digits here. And in particular, we include an extra digit for each clause. So we have 3 additional digits for each number, and we set that digit to 0 if the corresponding literal does not occur in the corresponding clause. And otherwise, if the literal does occur in the clause, we set it to 1. So for the first clause, for example, we have 3 literals, not x, y, and z. So we set the corresponding values to 1, and then set the others to 0. And then for the second clause, we have x, and not y and z, so we set those to 1, and we set everything else to 0. And then for the third one, in the same way, we set not x and not y and not z to 1, and x, y, and z to 0. Again, remember that these are not binary numbers, but decimal numbers. This is not obvious because we only used zeros and ones so far, but you should really read these as decimal numbers. So now, what we want is that if a clause is satisfied, we reach the target number in that particular position of the decimal number. So we have now here the 4th position, which corresponds to the first clause. And I want to make sure that if I select any of the literals belonging to that clause, then I reach my target number. This is a bit tricky, but for a moment assume that we could ask for inequalities in the target number capital W. So we would ask the first digit to be equal to 1, the second digit equal to 1, and the third digit equal to 1 as we had before. And we would ask for the 4th digit to be at least 1. If we could do this, then this would be easy, right? Because that would ensure that we pick either not x, y, or z. If we do this, we satisfy the condition. If we do not do this, then the clause is not satisfied, and we have no hope of reaching our target value capital W. And it would work the same way for C2 and C3. The problem here, of course, is that we cannot do this. Capital W needs to be a real number. We cannot include these inequalities as conditions here. So here's the idea. We know that there are 3 literals in each clause because we are talking about 3 set. And therefore, we know that if the clause is satisfied, I pick either 1, 2, or 3 of the correct literals. So the target value in that position of the decimal number will be 1, 2, or 3. I just don't quite know which one. But what I can do is I can now include additional dummy numbers in my input instance. So we add additional numbers. And in particular, I add 2 numbers for each clause. And both of those numbers will have a 1 in the corresponding column for that clause and zeros everywhere else. So these numbers can be included in the subset for SubsetSum or not. But if I only include those numbers, I have no hope to reach a value of 3 in that position. To reach a value of 3 in that position, I need to pick both of these numbers plus one number that belongs to a literal that occurs in the clause and therefore would satisfy the clause. Or I could pick only one of the dummy numbers and 2 of the literals that occur in the clause, and then the clause would also be satisfied, of course. But I could also not take any of the dummy numbers and take 3 literals that belong to the clause. All of those are possibilities to reach this target value. But if I don't take any of the literals that belong to a clause, I get 0 value from those, and then the dummy numbers can only get me up to 2, but not up to the target number 3. So I can only reach my target number if I select at least one of the literals that belong to the clause. Only then can I get to 3 in this particular column. And that finishes our construction. So again, for each variable and the negation of the variable, we introduce a number, and then we introduce 2 dummy numbers for each clause. And our target value is a series of 1s followed by a series of 3s, where the number of 1s corresponds to the number of variables in the formula, and the number of 3s correspond to the number of clauses in the formula. And now it's possible to find a subset that reaches the target number if and only if the 3-set formula is satisfiable. I said at some point that it's important that we don't have carryovers when we sum up some numbers here, and it's easy to convince yourself that this is really true. So for the columns that belong to variables, we always only have 2 numbers that have a 1 and everything else has a 0. So even if we sum up everything, we would get at most 2 and not have a carryover. And for the clause columns, we only have at most 1, 2, 3, 4, 5 entries that are 1, and everything else has to be 0. This is because we are talking about 3 satisfiability. So we know that each clause only contains up to 3 literals. And then we have, in addition to that, 2 dummy numbers. So in total, we can get to a value of up to 5. But still, we don't reach 10, so there is no carryover here. So let's quickly check that this reduction really works. If we have a satisfying assignment for our 3-set formula, then we can pick the corresponding numbers that correspond to the variables or the negation of the variables for our subset. And that would reach the correct target values for the columns that correspond to variables, because we always include either the variable or the negation of the variable. And we can also reach the target value for the other columns because we know that each clause is satisfied, and therefore so far in each of these columns we've had at least a value of 1. And if we don't have a value of 3 yet, we can include either 1 or 2 of the corresponding dummy variables. Now for the other direction, if we have a subset that sums up to exactly our target value, then there should also be a satisfying assignment. So what is a satisfying assignment? Well, so we take the subset that sums up to the target value. We know that that subset includes always, for each variable, either the number that corresponds to that variable or the negation of that variable, because we reach the correct target values in the first few columns here. And then we also know that we will satisfy all the clauses, because I know that for the columns that correspond to the clauses, I could have picked at most 2 of the dummy numbers, because there are only 2. And so to reach a value of 3, I would have to pick at least 1 more number, and this will be a variable or a negation of a variable that occurs in the clause, and therefore the clause is satisfied. This is also obviously a simple construction, so this can be done efficiently and in polynomial time. And also the size of the SubsetSum instance we construct is only polynomial. In the size of the 3-set input, we only have 2 dummy numbers for each clause and 2 numbers for each variable. And then the size of those numbers, each of them contains a number of digits, which is the number of variables plus the number of clauses. So in total, this is polynomial in the size of the input. There's one little problem here that you may have noticed, which is that the numbers we construct, some of them are identical. In particular, the dummy numbers, we always have two identical dummy numbers. In the definition of the subset sum problem, we said the input is a set of numbers. What we've constructed so far is really a multiset, so because we allow numbers to appear multiple times in the set. But there's a technical way to avoid this. The solution is to change the dummy numbers and change the target value. Rather than including two numbers that are identical, so we have 1 in one position and zeros everywhere else for both numbers, I will make one number to have a 1 there, and then I have a second number which has a 2 there. And then I change my target to 4 instead of 3. It's easy to verify that the general idea of the construction still works, so you can only get to 4 if you pick at least one literal that corresponds to a clause, because the dummy numbers would also only get you to 3 if you sum them up. And you can also always reach for. Like if we had 1 before, I pick 2 dummy numbers, they give me 1 and 2, so in total I get 1 plus 2, which is 4. If I had 2 before, I pick only the dummy number that has a 2, that gets me to 4. And if I had 3 before, then I pick only the dummy number that has a 1. So I also get to 4. So this is a small technicality that you shouldn't worry too much about. I just wanted to mention it for completeness.